The sequence of the events and the elements involved in LNG handling from liquefaction to consumption is called LNG supply chain.
Natural gas production is a process. It includes identifying fields, extracting the gas, and delivery to a processing plant. The pie chart shows the proven gas resources around the world as in January 2006.
Liquefaction plant. The gas is transferred to the liquefaction plant. Here, the gas is refined to remove impurities and then liquefied to LNG for more economic and easy transportation. It is stored in cargo tanks designed to withstand cryogenic temperatures.
Cooling to minus 161.5 degrees centigrade at atmospheric pressure reduces the gas to a liquid state, that is, 600 times of its original volume.
LNG carriers. The liquefied gas is then loaded on LNG carriers and transported to the receiving terminal. Regasification plant. Here, LNG is received and stored in cryogenic tanks. Based on demand, it is regasified using vaporizers and distributed to the utilities or end users. The main constituent of natural gas is methane, while the other constituents are ethane, nitrogen, propane, butane, pentane, and carbon dioxide. IGC code defines a liquefied gas as a product having a saturated vapor pressure of 2.8 bars absolute at 37.8 degrees centigrade. The critical temperature of methane is minus 82.5 degrees centigrade and critical pressure is 44.7 bars. Therefore, at 37.8 degrees centigrade, it can only exist as gas and not as a liquid. LNG is a clear, colorless, odorless, non-corrosive and non-toxic liquid. LNG vapors do not burn rapidly like gasoline, but forms a slow-burning flame that burns back to the source of the natural gas vapor. The table provides a summary of the physical properties of LNG. Methane in the form of LNG is carried at an optimum temperature of minus 161.5 degrees centigrade at a pressure slightly above atmospheric. It is obvious from the graph that if the cargo temperature was any higher, say minus 140 degrees centigrade, then the storage pressure will increase to 5 bar. The tanks have to be designed for a higher pressure, and still the volume of cargo transported will be lower.
The graphic shows the temperature at which the constituents of LNG liquefy or change from vapor to liquid at atmospheric pressure. You should know the boiling points of the constituents of natural gas to understand their behavior. The difference in boiling points affects the liquefaction process. It also may reflect in the change in concentration of the LNG during carriage. Methane has a low boiling point and vaporizes in normal atmospheric conditions.
The potential hazards of LNG are the result of its basic properties, including its cryogenic nature and dispersion and flammability characteristics, structural damage, asphyxia, fire risk, pollution, frostbite, rollover.
An LNG spill can cause brittle fracture on unprotected steel structures on board due to the coldness and uneven rate of contraction of the spilled surface. Structures which are likely to come into contact with LNG are made of cryogenic material, stainless steel or nickel steel or aluminum alloy. A minor leak will cause local icing.
The vapor cloud at a spill site can displace the air, including oxygen, causing asphyxia or lack of oxygen to any unprotected personnel. LNG is a clean, non-polluting product. When spilled into sea, it does not create any visible danger to the marine environment. Handling LNG without proper protective equipment can cause frostbite. All personnel must wear gloves, face masks, and other protective clothing as a protection from the freezing liquid when entering potentially hazardous areas. When LNG spills on water, the heat transfer from the water to the LNG is more rapid than it would be if the LNG spills on land. LNG rapidly vaporizes, releasing a large amount of energy when it does so. If the transformation is rapid enough and the volume is large enough, a flameless explosion called rapid phase transition (RPT) can occur. RPT does not involve combustion. Experience shows that RPTs represent a relatively minor risk with limited potential for damage to nearby equipment. Rollover occurs when unstable strata of LNG form within a storage tank. After a period of time, these strata may be spontaneously rolled over to stabilize the liquid in the tank. Such a rollover may lead to sudden vaporization, which may be too large to be released through the normal tank pressure release valves. At some point, the excess pressure can result in cracks or other structural failures in the tank. Procedures are adopted both on board and ashore to prevent rollover. Sophisticated containment systems prevent a leak or contact with an ignition source, which can lead to explosions from occurring. As LNG is stored at atmospheric pressure, a crack or a leak from the tank will not create an immediate explosion. In theory, an explosion cannot occur if oxygen content is less than 13% by volume, regardless of percentage of LNG. When LNG is released accidentally or during operations, as the vapor formed is colder and heavier than the surrounding air, it creates a fog or a vapor cloud above the released liquid. As it warms up, this cloud will disperse. The vapor cloud will only ignite if it encounters an ignition source while concentrated within its flammability range. Safety devices and operational procedures minimize the probability of a release and subsequent vapor cloud formation. The upper and lower flammable limit of LNG are 15% and 5.3% by volume respectively. LNG vapor is lighter than air at vapor temperature greater than -110 degrees centigrade and heavier at vapor temperature below -110 degrees centigrade. Thus, if LNG spills and the air movement is little, a flammable mixture that can be easily ignited may be formed.